Hello everyone. Myself is Rajesh KS, Assistant Professor, Department of Electrical and Electronics Engineering, Madanapalle Institute of Technology and Science, Madanapalle. In this session, we are going to discuss with respect to bipolar junction transistor regarding the fundamental concepts and also the biasing concepts. So this is how the flow of the presentation will be. Introduction, bipolar junction transistor, the basic concepts, and we are going to discuss with respect to the BJT biasing concepts. And in case of biasing, we have different types of configurations, that is biasing configurations. But in this session, we are concentrating on fixed bias configuration, and we're going to solve one problem with respect to fixed bias configuration, summary, and the reference. So in case of the electronic concepts, so transistor we are going to use for mainly the amplification function, and also in some cases we are going to use as a switch. In case of a switch, it is going to have two states. One is like on condition and also during off condition. So mainly we are going with amplification and all switch functions. And with coming to the application related, we are going to use in case of mobile phones, radio frequencies, televisions, and industrial applications. And while coming to the transistor family, we have different types of transistors like bipolar junction transistor, metal oxide semiconductor field effect transistor, insulated gate bipolar transistor. These are the main transistor where we are going to use in case of electronics concepts. And in this session, we are concentrating on bipolar junction transistor. Normally, we represent as BJT. While coming to BJT, it is a three-terminal device. The terms we are going to represent as base, collector, emitter. And while coming to the symbol, how we represent the BJT, so this is going to look like this. So this is a symbol we represent for the BJT, bipolar junction transistor. This is the base terminal. In short, we are going to represent as B, and this is collector terminal. We are going to represent as C, and this is emitter terminal. It is having three terminal semiconductor device. And while coming to the BJT, we have two types of BJT based on the direction of the current flow and also based on the structure. So the symbol what we represented here, we call this one as NPN transistor or NPN BJT. Okay, this is the symbol with respect to NPN transistor. And we have one more type of transistor or BJT. So the symbol with respect to that we represent like this. This is base, this is collector, this is emitter, and the current flow will be like this. This is, we call it as a PNP BJT or PNP transistor. The arrow mark indicating here, it indicates the direction of the current flow. Okay, based on the direction of the current flow, we have two types of, one is we call as NPN transistor, another one is PNP transistor. And it is three-layer device. So three-layer device means the structure is having three layers. So one is we call it as P layer, other one we call it as N layer, and this is P layer, which means that this is made up of positive layer, negative layer, and this is also positive layer. So the center layer, N layer, we call it as base, and this is emitter, and this one we call it as collector. So this is PNP transistor, and we have one more type, that is NPN. So this layer is N, and this layer is P, and this layer is also N. So this N layer we call it as collector, the center P layer we call it as base, and this N layer, this terminal is called as emitter. So as I said, we have two types of BJTs. One is PNP, another one is NPN. So here this transistor is having three layers, which is made up of P layers and N layers. So this is how the symbol and the structure is going to look like with respect to BJT. And one more important thing is, in this case, this BJT is having two junctions. So I'll mention this is as junction 1, which is present between base and emitter terminal. Normally we represent as base to emitter junction. And other junction which is present between collector to base. This is we called as junction 2. So in case of this bipolar junction transistor, that is BJT, so it is having two junctions. Normally we can define the BJT as a 3-terminal, 3-layer, 2-junction semiconductor device. So this is how it is going to look like. So I'm going to remove all those things. So this is the symbol representation with respect to NPN and PNP. And as I said, this is the structure, how we represent for the two types of transistors, NPN and PNP transistors. And as I said, it is having 3 layers, and the two junctions we name it as collector to base junction and base to emitter junction. And the next thing we are going to have is the biasing. So here in case of the BJT, we are going to have two types of analysis. One is DC analysis, other one we called as a AC analysis. So in case of DC analysis, we are going to do the biasing, that is by giving the DC supply. So biasing indicates that is nothing but to determine operating point of the transistor. So to obtain operating point of the transistor, we call it as a biasing. So here operating point indicates that is nothing but the operating voltage and operating current. So as we know that we have three terminals in case of BJT. So one is we called as collector current, the current flowing through the collector terminal. That normally we represent as output current. So this is one parameter that is in case of operating point. And other one we have is collector to emitter voltage, that is output voltage. So biasing we are going to do to determine the operating point of a transistor. So based on this operating point of a transistor, we can know that, or we can decide that in which region it is operating. Okay. So while coming to the operating regions of transistor, we have three types of operating regions. So we'll see one by one. So as I said, the main aim of biasing of the transistor is to obtain collector to emitter voltage and the collector current. So as I said, we have three operating regions in case of the transistor. So one is we call it as cutoff region, active region, and other one we call it as saturation region. So here in case of cutoff region, and as I said in the previous slide, we have two junctions in case of BJT. One is we call it as emitter to base or base to emitter junction and collector to base junction. So in case of cutoff region, these two junctions are in reverse bias condition, which means that so the reverse voltage will be applied in case of this cutoff region. So due to this reverse bias condition of both the junctions, it is going to act as a off switch in case of cutoff region. While coming to the active region, the emitter to base junction is forward bias and the collector to base junction is reverse bias. And in order to perform as an amplifier, we need to operate the transistor in active region. So whenever the transistor operates in active region, it works as an amplifier circuit. So which means the output signal will be increased, or the magnitude of output signal will be amplified with respect to the input signal. And one more operating region we have is the saturation region. In case of saturation region, the emitter to base junction is forward bias and also collector to base junction is also forward bias. and it is going to act as a on switch. So these are the different functions which is happening for transistor in different operating regions. And one more thing is, based on the region in which it is operating, the function will be performed, and we need to choose the proper operating region in order to obtain these different functions here. And while coming to the biasing, we have different types of biasing in order to obtain the operating point. So that is collector current and also the collector to emitter voltage. So the first and the basic biasing concept we have is fixed bias configuration, emitter stabilized bias configuration, collector to base bias configuration, and we have voltage divider bias configuration. So these are different biasing configurations. All these biasing configuration here is to determine the operating point, that is nothing but collector current, and also the collector to emitter voltage. So other and some small changes is there with respect to the stability of operating point in each and every configuration. In this video session, we are concentrating on fixed bias configuration. How exactly this fixed bias configuration will be done, and the circuit and how the analysis is going to be done. So this is the circuit how we represent for the fixed bias configuration. So here this is the transistor. This terminal represents base, this is collector, and this terminal represents emitter. And this is NPN transistor. So the current flow is indicating this direction, which indicates it is NPN type of transistor. We are using the resistance here, collector resistance. RC represents collector resistance, RB represents base resistance, and the current flowing through these resistance, that is IC represents collector current, RB IB represents the base current, and here IE represents the emitter current. And this configuration what we are using in case of transistor, we call it as a common emitter configuration. So common emitter configuration means the emitter terminal will be common for both, that is base as well as collector. The base will act as a input terminal and the collector will act as a output terminal. So this configuration we are using, we call it as a common emitter configuration. In amplification purpose, we are going to prefer this type of configuration. And also we are going to use the capacitors to the input side and also to the output side. So these capacitors, we call it as a coupling capacitors. So the main function of these coupling capacitors is to block the DC, and it will pass only the AC during the amplification purpose. Okay. And here we are mainly concentrating on biasing, which means that we are going to do the DC analysis here. And we already know that the capacitive reactance. So capacitive reactance we indicate as XC, which is nothing but 1 divided by omega C. So the omega indicates 2 pi F into C. And in case of DC analysis, the frequency will be 0. So this capacitive reactance will be infinity, which means that the voltage drop across these capacitance will be in higher value. So due to that, these capacitors will act as a open circuit in case of DC analysis. So that is main important concept in case of this biasing. So which means we are not going to consider the effect of these capacitors in case of DC analysis. These capacitors will act as a open circuit. So and V naught the represents output voltage and V in represents the input voltage, and this VCC represents the DC supply which is given for the biasing. So we'll see the analysis, the DC analysis with respect to this fixed bias configuration. So C1 and C2 both are coupling capacitors. VCC is the supply voltage, RB represents base resistance, RC represents collector resistance. So as I said, we are going to consider the capacitors as open circuit in case of DC analysis. And while coming to the next slide, we have the DC equivalent circuit. As I said, we are not going to consider the capacitors. We are going to keep it as a open circuit. And the main intention of the biasing concept is to determine the operating point of the transistor. So the operating point of the transistor is nothing but to determine the collector current and the collector to emitter voltage. So we need to derive the equation for these two parameters in case of this fixed bias configuration. So in order to obtain the collector current, so we have the current gain equation. So this configuration what we are using is common emitter configuration. The current gain in case of the common emitter configuration we represent as beta. So which is nothing but output current divided by input current. So in case of common emitter configuration, the collector is going to act as a output terminal and the base will act as a input terminal. So the output current is the IC, the collector current, and the input current is IB, the base current. So current gain in case of the fixed bias configuration is given by IC divided by IB. So from this equation, we can obtain the collector current IC equals to beta times IB. So in order to find the collector current, we need the base current and also the beta, that is nothing but current gain. So from this equation, once we know the value of base current, we can find the collector current. So to determine the base current, we are going to apply the KVL for the base circuit. Base circuit means the base circuit which is having RB resistance and the supply. So by applying KVL, so we are going to determine the equation for the base current. So once you apply the KVL here, this is plus VCC, this is at positive potential, and the current is moving in this direction. So we know that the current will move from higher potential to lower potential. We are going to consider this as plus and this as minus. And this junction, we call it as base to emitter junction. The voltage across base to emitter junction we represent as VBE. And so the emitter is connected to the ground potential. So for this circuit, base circuit, we are going to apply the KVL. Once you apply the KVL, we get the equation as VCC and minus the voltage drop across this resistance is IB into RB, and the voltage across base to emitter junction is minus VBE, that should be equals to 0. So from this equation, we can obtain the base current, that is IB, as VCC minus VBE divided by RB. So this VCC indicates the supply voltage. So this VBE represents base to emitter junction voltage drop. So this base to emitter junction voltage drop, it is based on the type of transistor we use. Like if it is made up of silicon, normally we take as 0.7 volts. If it is made up of germanium, we are going to consider as 0.3 volts. And divided by RB represents the base resistance. So this is equation to obtain the base current. Once you know the base current, we can determine the collector current as beta times IB. So IC equals to beta IB. So this is one operating point parameter, that is collector current. So to determine collector current, we are going to apply KVL for the base circuit. So this is one point. And in order to find other operating point, which is nothing but VCE, so we need to apply KVL for the collector circuit or the output circuit. So the voltage at this collector point, that is here, is plus VCC, and the drop current is flowing in this direction. This is at positive potential, this is at negative potential, and here the emitter current which is going to the ground potential. So when you apply KVL for this collector circuit, we obtain equation as, so VCC, so this is simplified equation. So we obtain equation as VCC Here the current is moving from higher potential to lower potential, minus IC into RC, and here the voltage, this is plus and this is minus, we get minus VCE. That should be equals to 0. So based on this equation, we get VCE equals to VCC minus IC into RC. So after obtaining the value of IC from this equation, we will substitute in this here to obtain the collector to emitter voltage. So this is how to obtain the operating point parameters in case of fixed bias configuration. And this is a very basic biasing configuration and very simple biasing configuration to determine operating point of a transistor. So based on these two parameters, we can decide that or in which region the transistor will be operating, whether it is in cutoff region or it is in active region or in saturation region. But for amplification purpose, we need to see that the transistor should operate in the active region. And by using these equations, we'll simplify one problem on the fixed bias configuration. So this is a given problem. So for fixed bias configuration, this is a given circuit and some of the parameters is given. VBE, base to emitter junction voltage drop 0.7 volts, and the current gain is given beta 60. And in the circuit, so here base resistance is 220 kilo ohm, the collector resistance is 2 kilo ohm, and the coupling capacitors is given, which is 10 microfarad. So for this problem, we need to find quiescent values. Quiescent values, that is also nothing but we call it as a Q point values or operating point values. That is nothing but we need to find the base current and collector current. Okay. And the second we need to find is collector to emitter voltage we need to determine, and base to ground voltage, collector to ground voltages. Base to ground, so that indicates we need to find VB, and collector to ground, that represents VC. From this collector terminal to ground and from this base terminal to ground, we need to find these two voltages, and the voltage between base and collector, that is VBC, we need to find. And once the beta changes, that is current gain changes, how the operating point is also going to change. So we need to find the new values of IC and VCE for other value of beta which is 110. So we'll see step by step procedure. So let's first make a note of the given data what is available in the circuit. So the supply voltage is also provided, which is nothing but 10 volts. So base resistance is 220 kilo ohm, collector resistance is given 2 kilo ohm, and the coupling capacitors is provided, that is 10 microfarad. And as I said, in case of this DC analysis, we are not going to consider these coupling capacitors. So the first parameter we need to find is the operating point values with respect to the base current we need to find and the collector current we need to find. So in the previous slides, we have obtained the equation with respect to collector current, that is beta times IB. So beta is given, which is nothing but 60, the first case. So in order to obtain the collector current, first we need to determine the base current. So base current equation we seen in the previous slide, which is nothing but VCC minus VBE divided by RB, that is base resistance. VCC is nothing but the 10 volts which is provided, and VBE is nothing but 0.7 volts which is given in the problem itself, and RB represents the base resistance which is 220 kilo ohm. So by using these values we can obtain the base current. Okay, so we'll substitute and we'll simplify what will be the answer we are going to obtain. Okay, so this is the equation for the base current, and after substituting the values with respect to VCC and VBA, we obtain the base current as 42.27 microamps. So normally the base current will be in terms of microamps. Once you obtain the base current, so as we know that the relation for collector current will be beta times of IBQ. That is nothing but IBQ represents the base current at quiescent point. That is nothing but operating point. So beta is provided 60 multiplied by the base current value 42.27 microamps. We get the collector current as 2.54 milliamps. So here in many cases the collector current will be in terms of milliamps and the base current will be in terms of microamps. So this is the first parameter we need to find, that is base current and the collector current. So the next operating point we need to find is the VC, that is nothing but collector to emitter voltage. So while doing the derivation with respect to fixed bias configuration, we obtained equation with respect to VCE as VCE equals to VCC minus IC into RC. So by using this equation or by using this relation, we can determine the collector to emitter voltage. So VCC is given, that is 10 volts, and collector current we determined in the previous step, that is 2.54 milliamps, and RC is given, that is 2 kilo ohms. So by using this relation, we can obtain the collector to emitter voltage. That is one more parameter with respect to operating point. So you obtained as operating point is 4.92 volts by using VCC minus IC into RC. The next parameter we need to find is the voltages with respect to ground. So one is base to ground voltage and collector to ground voltage. So with respect, you can observe in this circuit, so this is the base terminal and this is the collector terminal. So the voltage at this point we are going to consider as VB, and this is the ground potential. That is nothing but emitter is connected to the ground potential. So by observing this circuit, whatever voltage present across this base terminal, the voltage is getting drop across this base to emitter junction. So we can write as VB is equals to VBE. So based on this circuit, so VB is equals to VBE, which is already provided. It is nothing but 0.7 volts. And even with respect to the collector terminal, voltage at this collector terminal, we are going to consider as VC, and the emitter is at the ground potential. Whatever voltage present at this point, all voltage is coming across this collector to emitter terminals. So we can write VCE is equal to VC equals to VCE. So VCE we determined in the previous step, which is nothing but 4.92 volts. This is how to find the ground voltages. And the next parameter we need to find is base to collector voltage, which is nothing but VBC. So the relation for this VBC is nothing but VB voltage at base terminal minus VC voltage at collector terminal. By using these two parameters, we can find the voltage of base to collector junction. So we obtained that value as minus 4.22 volts. So VBC is nothing but base to collector voltage. So by using this relation, we are going to find base to collector voltage. And the last parameter we need to find is the operating point values. That is nothing but IC and VCE when beta changes. So in the previous case, the beta is given is 60. So in this case, the beta is changed to 110. And we have seen the base current equation. IB is equals to VCC minus VBE divided by RB. So in this case, here we don't have any beta parameter in this base current equation. So the beta will not going to affect, the base current will not going to affect by changing in the beta value. So here the collector current is going to change. Once the collector current is going to change, collector to emitter voltage also will change. Whenever beta is going to change, these two parameters will lead in changing. So we'll see that one by one. So whenever the beta changes, the new collector current value is given by IC equals to beta times IBQ. So with respect to IB, we are going to consider the previous value only, that is 42.27 microamps. And in this case, the beta is 110. But in previous case, it is 60, but here it is 110. So after substituting these two parameters, we obtain the collector current as 4.65 milliamps. And while coming to the collector to emitter voltage, the same relation what we used in previous case, VCC minus IC into RC. So here VCC is 10 volts and IC, the new IC value we need to substitute here, which is nothing but 4.65 milliamps, and the collector resistance is 2.2 kilo ohms, which is nothing but 0.7 volts. So whenever beta changes, the collector current changes, and also the collector to emitter voltage also changes. But the base current will not going to change by changing in the beta value. So this is one of the problem which we are going to solve on the fixed bias configuration. So in this session, we have done with respect to fixed bias configuration on one problem on that. In upcoming video sessions, we are concentrating on other type of biasing configurations like emitter stabilized bias configuration, voltage divider bias configurations, those things. And while coming to the summary of this session, we are concentrated or we are discussed with respect to the transistor and the different type of transistors we have. Mainly the in this session where we have done on the BJT. So BJT is a three terminal device. The terminals we are going to indicate as base, collector, emitter, and it is having three layers and two junctions. So the two junctions we are going to indicate as collector to base junction and base to emitter junction. And one more concept we have seen here is the biasing. So the main intention is to do the biasing here is to determine the operating point of a transistor, in which region it is operating, whether it is in cutoff region, saturation region, or active region. In order to perform as an amplifier as a function, we need to operate in active region. And in order to operate as a switch, so as we know that switch is having two states, on and off. In order to perform as off switch, we need to operate in the cutoff region. In order to perform as on switch, we need to operate in the saturation region. So, but in this case, the application we are concentrating is for amplification. So for that, we need to operate the transistor in the active region. That is comes under the biasing concept. And we have different types of biasing like fixed bias configuration, voltage divider bias configuration, emitter stabilized bias configuration, collector to base bias configuration, those things and all. And also in this session, we have seen one problem on fixed bias configuration, and we have derived the equations with respect to the operating point for fixed bias configurations. Okay. So this is a reference what I have used for this presentation. Okay. Thank you.